Okay, so the force, the actual force between two charges. The equation is called Coulomb's law. After Mr. Coulomb. The force exerted on a charge. We have a constant. It's called the electric constant. It's actually an abbreviation of a couple other constants. Turns out we see this epsilon naught. Epsilon naught, I can't remember, it's called, I think it's the permittivity of free space or permeability, I can't remember which is which. But it's a constant. It's a constant we will see a lot in relation to electricity. It's in the front cover of your book. It's not something you have to memorize. Units are Coulomb squared over Newton meter squared. So epsilon naught will show up in a lot of the equations that we will use for electricity. It turns out this quantity 1 over 4 pi epsilon naught shows up in a lot of equations. So someone got really tired of writing 1 over 4 pi epsilon naught and said, you know what, let's just call it k. Make it a constant. When we plug in 1 over 4 pi epsilon naught, it comes out to be 8.99 times 10 to the 9th. Units are Newton meter squared per Coulomb squared, which, by the way, this is close enough to be 9. A lot of times we'll just use 9 times 10 to the 9th. So that k is actually a very large number. That constant is very big. The quantities, the actual physical quantities that help determine the force are the charges involved. Now, we're going to use the magnitude of the charges, and I'll explain to you why. So Q1 and Q2 just represent the force, the amount of charge each of your little objects have. So if I have two little objects, one of them's Q1, that means how much excess charge, how much net charge that object has. And one Q2 would be the charge of the other one. They can be positive, they can be negative. It doesn't really matter. But we're going to use their magnitudes in determining the magnitude of the force. The other piece of information that's important is the distance between them. Center to center. Okay. This is an inverse square law. That means if the distance doubles, the force decreases by a factor of 4. If the distance triples, the force decreases by a factor of 9. You have to square that change in distance.
Yeah, it looks awfully like Newton's law of gravitation.
Exactly. It looks very, very similar to Newton's law of gravitation. Change out our Q's for masses and change out the constant. We'd have it exactly right. This equation gives us the magnitude of the force. It will tell us how big the force is on our charge. So for example, let's say Q1 was positive 3 nanocoulombs. I'm just making something up, obviously. Q2 negative 2 nanocoulombs. Plugging it through our equation, our K being 9 times 10 to the 9th, times our 3 nanos times 10 to the negative 9. I'm just going to use the magnitude, so times the 2 times 10 to the negative 9. Divided by, I guess we need a distance. That would be helpful. Let's say they're 1 millimeter apart. So 1 exponent negative 3 quantity squared. The magnitude of our force is going to equal 0.054 newtons. Unit-wise, Our K has units of Newton meters squared per Coulomb squared. Our two charges have units of coulombs. Our distance, once we square it, will have meters squared. The coulombs cancel, the meter squared cancels, and it leaves us with newtons, which is a good thing since we know forces in newtons. So the magnitude, that means this charge pulls on this charge with a force of 0.054 newtons. But that also means that this one pulls on this one with a force of 0.054 newtons. Newton's third law. For every action, there's an equal and opposite reaction. So even though they don't have the same magnitude of charge, the force they exert on each other is the same. Now, keep in mind force is a vector. If it might have been a little while since you've used vectors, you may need to brush up. Vectors, remember, we write in terms of their components or in terms of magnitude and direction. This one, all we need to do is tag on an I hat and we're good. We've got it in vector notation. This one, since it's pointing to the left, would be negative I hat. Notice, if we had plugged in the actual values and not just the absolute values, we would have gotten a negative answer. But that doesn't mean this force is in the negative direction. This force is in the positive direction. This force is in the negative direction, so that would have worked. So what we're going to do is we're going to find the magnitude of our force using absolute values, and then we're going to put the correct vector components on it. We're going to break it into its correct x, y, and z components. The way you'll see this written in the book and in the test notes is like this. Here's the magnitude. That's the magnitude of the force. R hat is a unit vector. What it means is it points radially away. It's in the radial direction. The R hat is to serve the purpose of reminding us to write it as a vector. R hat may have x components. It may be just x components. In the case of this example, R hat was I hat for this guy. R hat was negative I hat for this guy. So R hat is just to remind us to write our force as a vector, to find its x and its y components. Okay? We won't get three-dimensional on you, so you don't have to worry about z components. But it's going to be important to write your forces vectors, because if you have multiple charges, say we have those two, but we have another charge down here as well. And let's say we wanted to know the force on this guy. Well, we already know this left one is pulling this one to the left. What will this charge do to it? Pull it down. Well, to find the net force, on it, we need to add the forces. We need to use this equation individually, F1 plus F2. Keep in mind, when you have vectors, you can only add x components together. You can only add y components together. Our resultant vector will be right there. So that will be the net force on our charge. So we need to be able to write our forces in vector notation in order to accurately describe the net force, in order to add them together to get a result. Let's go ahead and figure this one out. Let's say this was 4 nanocoulombs. So we already know this one. To find the force between these two charges, we just use these two charges and the distance between them. Let's be boring and make it the same distance away. This force, all we need to do is find the magnitude. So the K, Q1 and Q2 are these two charges, the two charges involved in the force. And then R is the distance apart. So sorry, forgot my negative signs on my nanos. This force is 0.072, and it's in the negative j hat direction. So our net force, when we add these two vectors together, well, we only have one x component, so negative 0.054 newtons I hat minus 0.072 newtons j hat. This would be our net force. This is vector notation, writing it in terms of its components. We need to also be able to find magnitude and direction, meaning how long is this hypotenuse, this actual vector, and at what angle is it. So if we know the two sides, so our force basically is to the left 0.054 newtons, down 0.072 newtons. So the hypotenuse is simply found by the Pythagorean theorem. So the square root of 0.072 squared plus 0.054 squared. That's convenient. 0.09 newtons. So that's the magnitude. Direction, angle, we know the tangent of theta is the opposite side, so 0.072 newtons over the adjacent side, 0.054 newtons. So the inverse tangent of 0.072 divided by 0.054, theta is 53 degrees. So 53 degrees below the negative x-axis would be our angle.
Do you care which axis we measure it from?
If you write your angle just as an angle here, it's always implied to be from the positive x-axis. As long as you clarify, I don't care. So if you say 53 below negative x-axis, that's perfectly fine. But if you left it as 53, I would assume it was up in the first quadrant. Because all the magnitude and direction are your polar coordinates. So the polar coordinates are always measured from positive x-axis. So you'll need to do a little practice, remind yourself of vectors, adding them up vectorially. We'll do a few problems where we have multiple charges. Nice thing is you simply need to add them together, but before you can add them together, they need to be in vector notation. Please keep in mind, this equation is only valid for point charges, meaning the charge is concentrated at a dot, or for spheres of charge. It actually works for spheres as well. So it would work fairly well for our Van de Graaff. It's pretty spherical. It's not perfect, but it's close. Okay.